So basically, we will first discuss what a centroid of a tree is. A tree is a connected graph in which we can travel between any two nodes, and there's exactly one path between them. I will give an example. Like this is a tree of 5 nodes. 1, 2, 3, 4, 5. And there's exactly one path between them. And there are exactly n minus 1 edges where n is the number of nodes. So centroid of a tree is a node such that all the subtrees which hang from it have size at most n by 2. So here, this node, let this be the centroid. Let's denote it by C. And these are the subtrees hanging from it. Like there are three edges from that node, and there are three subtrees hanging from it. I will give you an example. Like in this tree, this node is a centroid. Since there are no, wait, no, this is not the centroid actually. This node is the centroid. Since there are exactly at most n by 2 nodes hanging from it. Like n is equal to 5. And we have two nodes over here, one node over here, and one node over here. So first we will show that each node, each tree has at least one centroid. So let this be the root node of a tree. The size of this, the subtree below this is obviously at n. Now, if it's any of its children has size more than n by 2, like let these be the children of it. Now, at most one child can have a size, subtree size more than n by 2. Since if 2 have it, then n by 2 x is greater than n by 2, y is greater than n by 2, then x plus y will be more than n, which is not possible since the number of nodes in the tree is n, and these are separate nodes. So like let this be the node with more than n by 2 nodes in its subtree. And we will keep going like this. So that like this node might have size more than n by 2. We will add more nodes here. You can imagine some more nodes over here. And we will reach a point where there are no more children with size more than n by 2. This node will be the centroid. Let's prove it. So this node has size greater than n by 2, subtree size. But there are no children which have size more than n by 2. This means that all the subtrees hanging below it have size at most n by 2. Now we have to show that the subtree over here is also at most n by 2. Now, since the subtree size of this is greater than n by 2, the number of nodes outside of the subtree is obviously less than n by 2. Since n minus n by 2. Now we will also show that a tree can have at most 2 centroid nodes. And if there exist 2 centroid nodes, they are attached by an edge. And there's a case where there's only one centroid node. There cannot be any other case. So let's suppose we have reached this node C1. Now, none of its subtree can have be a centroid. since the number of nodes outside it will always be greater than n by 2. Now we will see the parent of it. Let there be x nodes over here. We will actually rephrase this to more than or equal to n by 2 instead, so that the equality case is also there. If you all have any questions till now, you can ask.
Yeah, till now.
You have a question?
No, no, I'm just saying clear till now.
Okay. So let's suppose a tree has this centroid over here, and let these be the subtrees hanging outside it. Now the size of any of these, let the subtree size is denoted by S1, S2, S3, and till so on till Sk, where k is the number of children. Now Si is at most n by 2. Now for a node which is not a direct child of this, it can never be the centroid. Since there are at most n by minus n by 2 minus 1 nodes in its subtree. Like a direct child of this will have at most n by 2 minus 1. Minus 1 is for this nodes in its subtree. And hence greater than n by 2 plus 1 nodes outside it. This contradicts the information of the definition of centroid. So now we have to consider the k nodes over here. This is for the proof that there cannot be more than 2 centroids. Now the size of this is at most n by 2. However, if it has to be exactly n by 2 now, since we showed that if the size is this, then the centroid is violated condition. Now there can be exactly at most one the direct child which has size at exactly n by 2. Since if two child have, then the number of nodes will be n over here, but this does not include the centroid node. And this means that the number of nodes is more than n, which is not possible. So at most one of these can be centroid. Is this proof clear of the two centroids?
It's we proved there can be at most 2 centroids, right?
Yes.
Okay.
And they are directly connected by an edge. In many trees, none of these nodes will be centroid and only this will be. So I showed the way to calculate the centroid by going down to the tree again and again till there's a child with subtree size more than n by 2. Now I will cover a problem. So the problem is you are given a tree of n vertices. Actually, we will ignore the condition n is even, since the problem can be solved even without it. So basically, you need to find a permutation of length n such that the ith value is not I, it's something else, and distance the sum of the distance between node I and node AI is maximized. So for example, I will give an example of distance. Like distance between these two nodes is the number of edges between on the path between them. So this is 1, 2, and 3. So distance between these two nodes is 3. And now I will also define the depth of a node as the number of nodes, number of edges between the root node and that node. So the depth of the root d is 0. But let this be node 5. d5 will be 2. Now distance between two nodes will be equal to dx plus dy this is a 2d lowest common ancestor, which I will define now. So basically, let these be the two nodes, and we will add more nodes over here. So distance between node 5 and let this be node 4. We'll erase these. The depth of this is now 3, since there are 3 edges on the path from the root to the node. And the distance of this is 2. Now let's define the lowest common ancestor as the deepest node in the tree, the node with the maximum depth basically, which is the ancestor of both the nodes. And a node is an ancestor of itself. Ancestor of a node is like it's a parent or a parent of a parent and so on. Like for node 5, this node, and this node are ancestors, these 3 nodes. And for node 4, this node and this node are ancestors. Now, these two are the common ancestors, and the lowest common ancestor is this. Did everyone understand the lowest common ancestor?
Yeah.
So now we can see that the distance between two nodes is depth of x plus depth of y minus 2 into depth of lowest common ancestor, LCA. This is because we take all the edges over here, and we subtract these edges which are not on the path, a simple path between them. And these are happened twice, so we subtracted 2 times the depth of the LCA. And now the problem asks us to maximize distance between the ith node and AI node and the summation of them. Now, since this is a permutation, we can expand this summation as summation depth I plus summation depth AI. This is minus 2 summation depth LCA of those two nodes. Now, if you notice, these two sums are fixed because this always goes from I from 1 to n. So it's basically summation of di, and this is fixed, constant term. It will be equal to d1 plus d2 dn. And this is also fixed. Since this is a permutation, all of these happen exist exactly once in it, and it's exactly same. So this is constant. We need to maximize this term. Since this is maximum and we are subtracting this, so we need to minimize the LCA. Minimize summation depth Did everyone understand this? Of that we only need to consider this term, depth of the LCA. If you have any questions, you can ask. Okay, so I will continue now.
Wait, so we have rooted it arbitrarily for now?
Let it be rooted at R. For some R. Yes. We
Okay,
will change the root later while solving.
okay.
So now the best case scenario would be for any R. For any R, it's better that we need to minimize this. And this is true for all R. And now the best case scenario is when depth of LC is 0. That means that the root is LC of those two nodes. And if all of these are 0, this will be 0 and the answer will be depth summation of the depths into 2.
But does
And
the
now,
summation of the depths change if you change the root node?
yes, like for now, let it be rooted at any R. We will decide the R later, but this is true for all R. But we need to maximize the distance, so we will try to show the R in such a way that we can get the depth of the LC to be 0. And this turns out that it is possible. So we will consider the centroid of the tree and root it on the centroid. All the nodes we will root it at the centroid. Like this node is the centroid. There are total 11 nodes in this tree, I think. Yes. And there are at most 5 nodes in each subtree. So this is the centroid node. Now we need to minimize depth of LCA of I and AIth node, where AI is a permutation. Now for them to be 0, the LCA must be the root node, which is the centroid for all pairs of I and AI. So now this turns out that it is possible. The size of each subtree is at most n by 2. Now we will consider the order of the depth first search of the nodes, the start times. I will explain the depth first search first. So in a depth first search, if there's a node, like let the function be fx, we will iterate through all the nodes which are adjacent to x. If b is not visited before, we will run fv. And the depth first order is like before iterating over the neighbors, we define Sx to be C. And then we increase C by 1. So C is 0 initially. So like for this tree, we will this will be 0. We will go over here. And then this will be 1. We will go over here. 2. We will come back, go over here. 3. Come back. Like there are no more nodes which can be visited. We go back again. This is 4. This is 5. And we go back over here. This is 6. We go back and then we go to a new neighbor. 7. So there are 11 nodes over here. 0 to 10 we have labeled. Did everyone understand the depth first search ordering?
Yes.
So like DFS is a very commonly used algorithm in graph theory for tree problems and non-tree problems as well. And now if we notice that the node I, a node with start time I, and node with start time I plus n by 2. If we consider these two nodes, you will notice that they are never in the same hanging subtree. Like if they are in the same size subtree, this means that the size of the subtree is greater than I plus n by 2 minus I plus 1. All the nodes between them also counted. which is not possible since this is the centroid node. All the nodes have subtree size at most n by 2. And now if you assign in this way for all I, if you assign this is I, this is the ith node x, and you set ax to the corresponding y. Now, since this is a cyclic shift of the array of the start times, this is a cyclic shift basically. And so AI is a permutation. We set ax equal to y. We calculate the y for every I. We iterate from I 0 to n minus 1. We find the corresponding x and y, and we set ax equal to y. Did everyone understand this one? The cyclic shift.
Yeah.
Okay, so I will continue. Now the lowest common ancestor will be the centroid node. This is because there are no two nodes in the same subtree. And since they are not in the same subtree, there cannot be a common ancestor which has depth more than 0, which is not the centroid. And so we have minimized the sum depth LCA to 0. And now our answer is summation DI plus summation DAI minus 2 DLCA is basically summation DI plus summation DAI. And this is basically, I will start over here, basically equal to 2 in the summation of depths. Like this, we had proven was an upper bound before, and this is the maximum value. So now we have solved the entire problem. This problem is from Baltic Olympiad in Informatics 2020. Like it's a half problem. There was also a problem where you have to find the minimum value. Basically
I
two
have a
subparts.
question.
Yes, you can ask.
What do you label zero as? Like, how do you relabel zero? The centroid node?
No, we don't label it 0. This is the start time in the depth first search. So basically, we run DFS at the root node, centroid. And like we go
No,
all the numbers and run
no,
DFS
that's
over.
okay. But like when we add n by 2 to everything, um, what do we just add n by 2 to the centroid node's value too?
No, we don't add n to this. We basically match the 0th node with the n by 2 node. Not this is not the number of the node, but the start time. So basically, start ith node will be assigned to the node. Like let the start time be j, and we this is not actually I plus n by 2, but we add a modulo n over here. I missed this.
Yeah, yeah.
And we take the floor over here, or seal will also work.
Also, like, by changing your root node, does it change summation di?
Yes, it would. But let us ignore the other roots, and if we root at this, like did you understand that this is a upper bound? This is true for all roots actually. We can find the upper bound and take the minimum of them.
Okay.
Like it also holds true that for a centroid, the sum of summation of the depths is minimum. It cannot be more than the summation of depths of any other node. This can be showed as if there is a node with subtree size greater than n by 2, we can go to that node and we will get a lesser summation of depth. This is because when we go to the node for more than n by 2 nodes, the depth is subtracted by 1, b minus minus, I will write. And for like the nodes over here, the depth is increased by 1, but these nodes are less than n by 2. And so the total depth is decreases. So this shows us that the centroid node has minimum sum of depths also. Though that's not required in this problem. Like, did you understand this?
Yeah.
I will cover another problem. This one is a hard problem. This is basically you are given n nodes. Basically, you're given a graph. It need not be a tree. For the tree, the problem is like much easier. And you are given three numbers A, B, C in increasing order, non-decreasing order, and the sum of them is n, where n is the number of nodes. You have to partition the n nodes into three sets. Wait one minute. You have to partition the n nodes into three sets. And the subgraphs of at least two of the sets are connected. I will give an example. If A is 1, B is 1, and C is 3 in this graph, we can give this node to A, this to B, and these three nodes to C. And if you notice that this is connected, and this is also connected. This means that you can travel from one node to another without crossing any node not in the set. And like in this graph partition, all three are connected, but we need only two to be connected, at least two. So three is fine. Now, if you notice that C is more than A or B or equal, it's always optimal to find connected sets of size A and size B instead. Did you all notice this? Understand the problem? Did you all understand the problem? Hello? Okay, so I will continue. Now, since A is at most B and B is at most C, summation is n. Now, this should be obvious that A is at most n by 3. And since B is at most C, B cannot be more than n by 2. Did you all get this?
Yeah.
Okay. So I think that first I should cover the tree problem first. Since then it will be easier to understand. This is a hard problem. Like in a tree, we need to find two connected components which nodes are disjoint, the set of nodes are disjoint, and the sizes are A and B. Basically, if we can find the connected sets, one of which has size at least A and one has size at least B, if we can partition the nodes into two sets, we can rephrase the problem basically. Partition into two sets, size is greater than A, and like T, let it be B. And we can easily find in a connected graph of size S, we can obviously find the connection of size A and size B. So now in a subtree, in a tree, there must be one edge. If we want to partition, there must be one edge such that there are nodes of one set on one side and nodes of other set on other side. basically there cannot be nodes of both the sets on one side. Like there must be at least one such edge. I think this should be obvious since this is a connected component. Like let this be a connected component. And now let this be another connected component. So and let the pair, let this be the pair of nodes which are closest in the tree by distance. And let these be the edges. So these all edges work on the path between the closest pair of nodes. And now if there is an edge such that the subtree size, let it be x, and of the remaining tree it is n by x, n minus x. If x is and y, not y, n minus x greater than b, we are done. And if the opposite is also true, it works like x is greater than b and y, not y, n minus x is at least a. So we can find we can solve the problem for a tree in linear time easily. Did you all get this? Hello? Did you all understand the solution if the graph is a tree?
Wait,
This is
I'm
a
a little
simulation.
confused. If there are like if there are any two edges which are vertex disjoint, then can't you like take two vertices in one which is connected because it has that edge, then two vertices in another, and then third doesn't need to be connected.
What exactly are you saying? Like there are many cases where this problem, the answer is no. It's not possible to partition.
No, so it's like if you have two edges which
Yes,
are connecting different set of vertices,
yes,
uh, and now I take A, like I set A as just these two vertices and B as those two other vertices and C as
yes.
everything else.
But no, the size should be exactly A and B and C. You are given
Uh,
ABC, like
oh,
you
you're
don't choose
given
that.
ABC. Okay, okay,
Yes,
okay, okay.
you are given, and the sizes should be exactly A, B, and C.
All right.
So did you get it for the tree part where we get an edge which separates the two components?
Yeah.
And we can do these simple checks. Like this can be done using a depth first search in linear time. We need to solve this problem in linear time. Like if we try exponential, it will be obvious. And now for the general graph, we will take a spanning tree. A spanning tree is basically uh, a tree where the edges are a subset of the original m edges, n minus one edges in the spanning tree. The graph you are given is connected. If the graph is not connected, then you can check separately. Are there two components of size at least 10, at least b? Or you can run the connected solution on each of them separately, basically. And there can be more edges over here. Like there might be edge between these two nodes, between these two nodes, between these two nodes, and so on. This is just an example. Now, so basically, we will use the fact that now these numbers hint us that we should think about the centroid node. Like let us root the tree at the centroid node. And now let us consider the subtree sizes S1, S2. I had used this terminology before also, S1. They are k direct children, and let the subtree sizes be S1, S2, Sk. Now if Si is greater than A for any I, and obviously Si is out at most n by 2. So if we assign the subtree of Si, we take the subtree of Si, like let it this be the one. If A is 3, like let us ignore this for the values, exact values. And the remaining size is at least n by 2. Since this is at most n by 2, let this be set A, and the remaining is set B. Size of A is at least A, and size of B is greater than n by 2 is greater than B. So we can find the connected component of size B in this, connected components of size A in this, and we can assign everything else to C. Did you all get the part if there's a node with subtree size at least A? Yeah. Okay, so the harder part of this problem is if the subtree sizes are all less than A. Si is less than A, which is at most n by 3. So subtree sizes are at less than n by 3. Now, we also need to think that there are more edges in this graph. If this was a tree and there is no a subtree with a size at least A, it is easy to see that there is no solution at all. Since there won't be any edge with size, subtree size at least A, the subtree below it, and rest at least B. So now we need to incorporate the remaining edges. Like let these be the some edges. This means that this is connected. S1 in a subtree of this is connected to subtree of this. So we basically build a new graph. We don't consider the edges from the centroid right now. Like we build a graph of k nodes. Actually, I will start it with you. Let's denote these subtrees by V1, V2. Si were the sizes. This is the entire subtree and not the number of nodes. And we build a new graph where if subtree I, like these are two nodes A and B, we will I will use some other numbers. X, Sj. There are two nodes A of this, say, and B of this, which are connected by an edge which is obviously not in the spanning tree. In this, we will add an edge from Vi to Vj. So there are key nodes, and we find the connected components in this The centroid is not part of any of these nodes. We are considering the graph other than the centroid part. Let there be an edge from here to here, an edge from here to here, and an edge from here to here, let's say. So these three are in the same component. These are in the same component. We find the sizes of them. Now the sizes is not these nodes, but the summation of the subtree sizes. So basically, if subtree sizes of ith node, so V1, V3, and V5 are connected. So we find S1 plus S3 plus S5, and so on for all the components. Now, there are two cases. Like, let there be now M components, not M, P components. General graph, let there be still Q components, and we denote them by P1, P2, PQ, and we find the subtree, the sizes, and we denote it by a capital S, SI. If SI is, so we now need to think how we can find sizes. If SI is less than A, is less than B for all I, this clearly means that if we exclude the centroid, we cannot find any subgraph which can be a connected set. And the centroid can be in exactly one set. We need two sets, A and B. This is size A, this is size at least A, this is size at least B. But if each connected component has size less than A, which is also at most B, we cannot find both the sets. We cannot find any set. But if there's a centroid node, one centroid node we are considering, but this can be a part of at least at most one of these. So there would be one set which does not have this size limit. And in this case, the answer is 0. Not possible. There does not exist a construction. Did you all get this? That no construction exists if none of the connected components have size at least A. Hello? Okay, so assume you all understood. I will continue. Now, I claim that if Si is greater than A, for some I, there exists a construction. Now, let the connected component be this V1, VB2, VB3, and so on. This is the ith component. These are basically subtrees. So each of them might have many nodes. This might have more, and so on. And all of their sizes is less than n by 3. This I had shown before. We are considering this case only. Since if A is at least n by 3, we are done. But I will elaborate on this. If there was a subtree before which is at least n by 3, then it will always also be at least A, and we are done by the previous method we found over here. That if it is at least A, any of these subtrees, we can assign it this to A and the rest to B. This was done over here. This to A and this to B. Now, since Si, the smaller Si is less than A, is less than n by 3, This means that the subtree sizes is less than n by 3 individual subtrees. The connected subtrees size is at least a. And so now we run a depth first search on this graph of Vi. And as soon as we reach a location where the total number of nodes now is at least a, we exit. I will show. We don't take all of these. We take only some. Like there's a depth first search we do. And so like if we go from here to here and the total number of nodes SVB1 plus SVBK and so on, if this is at least A, we exit. Now the number of nodes is at least A, let it be X, at least A, and now we will show that it is at most 2n by 3, less than that. So this is the first instance where the size is at least A. So it was let the new was size be Y, the node we have added. X minus Y is less than A. Is less than n by 3. And now Y is also less than n by 3. Obviously, we had shown all the nodes are. And so X plus Y minus Y is at most, wait, so the size now, which is X plus Y, this is less than n by 3, and this is also less than n by 3. So we get this is less than 2n by 3. So the size is now in the range n by 3 to n by 3. Now there are two cases. Did you all get this? Hello? Hello? Is my voice coming?
Yeah, got it.
Okay. So now we have a connected component which is of size at least A. Now let this be the centroid and these be the children. Now suppose that in this where we exited in the previous depth first search, these few subtrees were considered and the rest weren't. These all are connected between each other without using the centroid in between themselves. And the size is at least A. And at most n by 2. Since this is case 1. So the size, the connect, like let it be T, this connected component T is greater than A. And now if we look at the remaining node, they are also connected through the centroid and through the respective subtrees. This is a connected. And the size, let it be Q. And Q is at least n by 2. We can show. Since this is at most n by 2, Q is at least n by 2. Which is in turn at least B. So we can find a set in this of size A, find a set B in this and assign the rest to C. This is at least A, this is at least B. We have partitioned into 2. So now we have solved for this. Did you all get this? Now the case 2 is very similar in fact. Now in this we find the sets T and Q. This is T, this is Q. Now T is at least n by 2, since this is the lower bound of the range. This is at least n by 2. And Q is at most n by 2. But we need to show it's always also at least A. Now since this is at most n 2n by 3, this is greater than n minus x. N minus 2n by 3, n by 3. This is greater at least A and this is at least B. Did you all get this? We have found a construction for this as well into two parts. One is at least A and one is at least B. So basically we have solved the entire problem. Since we have covered all the cases, we have solved the problem. Did you get the complete solution? Did you all get it? Hello? Did this problem is IOI 2019 split. And I've explained the entire solution. In most of the cases, there was a solution. The only case where there wasn't a solution was when the SI is less than A for all I in the graph of the VI. Did you all get the solution of this problem? Like if you have any doubts, you can ask and I can clarify since this is a pretty long solution. Hello? Did you all understand like other people also? So I can move on to the next problem. This is an IMO problem I will discuss. I am a shortlist actually. We'll decide which one we are. This problem which I am going to discuss is not much related to graph theory, but it is framed in such a way that it seems that it is graph theory. This is ISL 2005 C4. So you are given an integer n, and you are given a n nodes, and there's a edge between each of them. It's a complete graph basically, and there's a label. Each node is labeled, and from 1 to R, and each of the labels occurs at least once. Now the property is that if there are 3 nodes, 2 of the labels are same and one is different. A, let it be B, and A is greater than B for any 3 nodes. And we have to find the maximal R for which such a labeling is possible, and how many labelings are there for the maximal value of R. Not the total possible number of labels. Did everyone understand the problem? What the problem says? Hello?
Yeah,
How many people
I
are
got it.
still in the class? Like, are there any other people? Like, you can ask also if you have any doubts of the previous problems. So now we will try to make some observations. Like we will proceed in a general way and then come to the solution. Like let us look at the maximum value, maximum edge R. Now all the edges from this, like let this be a node. Exactly one of these two edges, one from between these two and one between these two, will be R. So we can find the set of nodes for which this is R. This is R. And the other, the cross edges between this and this will be something lesser. We can also see that no edges between these two will be R, and no edges between these two will also be R, since that will form a triangle with all edges same. Now, if there's a cross edge between these two, then it is still possible. If the diagonal edges, like in this quadrilateral, these four nodes, but if you see that this gets a little complicated, it's still possible to solve using this, but the solution is very long. So now if we can try the minimum value of the edge instead, we can try that. If this is 1, all the nodes, all the edges, since these are triangles basically, and the label of 2 is greater than label of the third, and 1 is minimum, all are greater and equal. So let this be A, this is A, and this is A is greater than 1. This is B, this is B, and B is greater than 1. So all these are same. If you notice that these two nodes, I, J, have exactly same value of labels to every node, every other n by minus 2 nodes. And it's exactly same. So now if we can think that if we can somehow proceed by induction for finding the maximum value of R, like let fx be the maximum value of R for x. And now like it's intuitive to think that it's x minus 1. We will show this later. It's intuitive. Like if we here also, if you see, this is 1 and no other edge incident to this is 1. Other edges can be 1 which are not incident to it, but I don't think it's optimal. So we will now merge these two nodes. We'll proceed by induction basically to show that it's x minus 1. So if n is 3, then this AAB, it's obvious that they are exactly two distinct values and R is equal to 2. Did you all get this part of the minimum edge and F3? We will merge the nodes I and J. We will merge them. Now, since the edges are same, exactly same, and we get a graph of size n minus 1. And if we proceed by induction, Fk is Fk minus 1. And we are finding Fk plus 1. If we find the minimum edge on this one, there's exactly 1. And we can show that it's at most 1 plus Fk. Since we assign a minimum edge and we contract the graph, we merge these two vertices and there at most Fk edges in the remaining graph. The graph retains all the properties, by the way, since the edges are exactly same. So Fk plus 1 is less than 1 plus k minus 1, which is k. So we will now show that it's exactly here. The construction is actually easy. We take any arbitrary edge, we assign it the minimum value 1, contract it. In the remaining graph, we choose a edge, we assign it value 2, we contract it. In the remaining graph, we assign 3 and we contract it, and so on till n minus 1. We assign the maximum value of R is n minus 1. This solves the A part of the problem. Did everyone understand the solution to this? Like I will proceed further. And now it turns out that for maximum value of R, how many labelings are possible? It turns out that for every new iteration of contracting, we need to assign a new minimum. If we don't assign a new minimum, the number of distinct values will be less than n minus 1. And that's not maximal. So if we define G, X as number of ways such that the maximum value of X minus 1 is attained, we choose a edge, X by 2. And we multiply it by Gx minus 1. In the contracted graph, we multiply the number of ways possible. And so this can be expanded x factorial, x minus 1 factorial. Since you see G3 equal to 3, G2 we will actually assume is equal to 1. So it can be easily shown that if we expand this x will come out as x factorial, x minus 1 will come out as x minus 1 factorial, and the 2 in the denominator of the combination will come out as 2 to the power n minus 1. This solves this problem basically. There are several different problems available, solutions available to this problem on AOPS, and you can also go through them. I can share the link. And now we can also discuss about general graph theoretic ideas. Like finding lowest common ancestor in optimal time. If we iterate over all the ancestors, like for a node I, we save the parent node I, and parent of root is obviously minus 1. It does not exist. And we can basically iterate over all the nodes and see which one is common to both the nodes A and B, and assign that as the LCA, the one with the maximum depth among all the common ancestors. But there can be n ancestors, up to n ancestors, n minus 1 ancestors. So it's not optimal. For each query, we are doing it in n ancestors, order n time. It's very slow. N comparisons we make to see, like we go over the depth, common ancestors at same depth, and see if they are same of these two nodes. And if they are same, we set it to that, and we don't go up the tree. But this is very slow. So now we will find a way to solve it in log n time, based to time with some pre-computation before the queries happen. So, like, do you have any ideas? You can also do it in root and time using some square root decomposition. So the log base 2 time, we will solve it using this way. We find the parent I, we find the parent, let parent ij be parent of I at j, which is j edges above that node. Basically, distance is j and that's an ancestor. We calculate this value for j equal to 1, j equal to 2, 4, and all powers of 2, 2 to the power k for the maximum k, which is at most n. Not at most n, like 2 to the power k is at most n. And now we can, it turns out that if there are n nodes, we can calculate this using n log n time. I will show how. This is called binary lifting, this technique. So parent I, instead of j, you I will change the terminology a bit. But it's actually fine. I will explain like this. This you already know before only. This can easily calculate it in linear time. Now parent, if we have calculated till k and we want parent I k plus 1, you can see that it is basically, you find the 2 to the power k parent and try to find the ancestor of that. So this is 2k above this is 2k above this. And so you can find the 2k ancestor by two computations. You go to this parent, and from that other node, you have computed till k for all nodes. You go up again. So in two operations, we can find the parent of that. I hope this is clear. And now, if you are given two nodes, A, B, and say B has more depth than A, without loss of generality, we go up till A such that the depth is same. Basically, we see the difference in depths y, and then we reach y nodes up. This is done by basically splitting y into its binary expansion. And we'll go to the power I power parent of b, and then so on. In log n, we reach at the same depth. The two nodes are at the same depth. It's possible that A is an ancestor of B and the node you reach over here is A only. In this case, the lowest common ancestor is A. But we can exit in this case. But if it's not, now we are at the same depth and we need to go find the lowest common ancestor. So we go in decreasing orders of powers of 2. Say n is 10 to the power 6. We go from 220 to 19 to 18 and so on. We compare the parent of the current nodes. Like current node 1 is A, current node 2 is B. Now, if the parent current 2J equal to parent curl 2J, this means that that is a common ancestor, but that may not be the lowest common ancestor. We aim to reach the node just below the lowest common ancestor. We aim to find cur over here and cur over here if this is the LCA. And then if we reach the node just below it, we can just query the parent directly. We will, if this is true, this condition, we don't change anything to current minus 2. We decrease j, we go to a smaller j. Now, if this is not true, this means that these nodes are not common ancestors and these are descendants of the LCA, and we can go up, up, and so on. We have currently, say, this is the fourth parent. This is also the fourth parent of this. But say this is, I will just give an example. Say distance between these two are 4, not this, 4, 2, 2, 4. Now, if we see the eighth ancestor, we will see that it is same or does not exist only if the depth of the tree is less of those two nodes. So we do not do anything. Now we go from 8 to 4. We go to these two nodes. Now these are different. We set A to this, B to this. Now it's 2. We see 2. The second ancestor is same for both. We do nothing. Now we go to 1. Now the this ancestor, the direct ancestor, is different. We set it to that. Now we have found the two nodes just below the LCA. We can directly query the parent of current, and this will be the lowest common ancestor. We make log 2 n comparisons. These two comparison. Log 2 over here and log 2 to reach the same depth. So it's order log 2 only. And now to show that this always happens, we always reach below this. We can see the binary expansion of the distance between A and LCA. Let this, not the binary formula, representation, we can see. You will see that we cannot exceed this. We don't see the binary representation of the depth directly. We see distance A, LCA, and -1. Binary representation of this is this. So if we try to increase it by this, the number cannot go more than that. It should reach this. We do nothing. Since this would exceed the depth and ancestors would be same. Now this one, if we consider this power, it we can add this actually. Since now the ancestors will be different. And so on we go. If this is 0, we obviously cannot do anything. Since the prefix is exactly same, we claim that. And if there's a 1, we can have to do that, since the parents will be different. And so when we reach there, we reach exactly this ancestor, and we can find query its direct ancestor, and we can find the lowest common ancestor. This takes log 2 time. And you can go over some code if you want. We do a depth first search first. Here we calculate the depth of the nodes, the direct parents. I had explained this in the previous problems, what depth first search is. And now, if the parents are calculated, we do the binary lifting recursion. Here we find the powers, uh, parents had powers of 2. Here J denotes the power. So J equal to 0 means direct ancestor. J equal to 2 means 2 square 4 ancestor. And so on. We do this recursion thing. And we set this like parent I to the power j is we go up 2 times basically. And now to calculate the LCA, we take the depth. We first make sure that the depth of A is at most the depth of B. B is at least that B. We find the difference. We find that parent. And now the two nodes are the same depth, which is what I discussed earlier. If they are the same, which means this is answer of this, we exit. Now, if they are not, we iterate over powers of the two and find the node just below the LCA. And now the nodes are just below the LCA at this line. And on this line, we return the direct parent and we find the LCA. If you can see, like this code is written if n is 5 lakh, and you can see that 2 to the power 20, which is more than 1 million, satisfies the problem. So we are essentially doing, you see 20 iterations of this, 20 of this. This is log. This is very efficient. And this way we can calculate the values very fast. So like if n is very large, like 1 million, and we have 1 million queries of LCA, then we have to do 10 to the power 12 comparisons, operations, and that will be too slow on this computer. It may run on a very fast supercomputer, but then you can increase the n. It won't work on this. Yeah, like it won't work even in 1,000 seconds. And now if we do this, there are 10 to the power 6 into 40 operations. And this is very small. So you can see a huge difference between these. As a homework exercise, you can try to find a way to solve this in root n, like exactly root n, not finding this and doing extra queries. So you can instead calculate the ancestors at the SQRT values, like root nth ancestor, 2 root n ancestor, 3 root n ancestor, and so on. You can go up. The same method will work. So I've covered everything I wanted to cover today. If you have any doubts in any of the problems or in the lowest common ancestor, you can ask. Hello, the class is over and I'm ending the session now.
Thank you for the class.